So today's topic is Kirchoff Laws. Kirchoff Laws are applicable to any DC circuit which consisting of batteries and resistors. The first one is called Junction Law. According to Junction Law, we have to draw first of all one small diagram here. Say some are currents drawn here towards and some are drawn here outwards. Say this is I1, I2, I3, I4, I5 and I6. We have seen that the current divides at P. This is center point P. Here we see that the current divides at this point P. The current drawn from the battery is equal to the sum of the currents through the resistors, and where P is called junction. The junction is a point where 3 or more conducting wires, here we have 1, 2, 3, 4, 5, 6 wires, where the 6 wires meet, that point is called junction. At any junction point in a circuit, at any junction point in a circuit, at any junction point in the circuit where the current can divide, where the current can divide, comma, the sum of the currents, the sum of the currents into the junction, must be equal to sum of the currents leaving the junction. Some of the currents leaving the junction. This means that there is no accumulation of electrical charges at any junction in a circuit. From the figure, I1 plus I2 plus I1 and I2 are inside, and one more is I4 is inverse, is equal to I3 plus I5 plus I6. The sum of the currents into the junction will be equal to sum of the currents leaving the junction. This law is based on conservation of charge. That means there is no accumulation of electrical charges at any junction in a circuit. This is called as law of conservation of charge. So this junction law is based on conservation of charge. The second law is known as loop law. For this, it's very important law. The first one is very simple to understand, but the second one is a little bit difficult. So listen carefully. The second law is known as loop law. Loop law. So the algebraic sum of increases and decreases in potential differences across the various components of the circuit in a closed loop must be 0. So that is the statement of Loops law. Let us write. The algebraic sum of increases and decreases in potential differences across various components of the circuit in a closed loop must be equal to 0. So let us imagine a circuit loop. The potential difference between the 2 points at the beginning of the loop has a certain value, and as we move around the circuit loop and measure the potential difference across each component in the loop, the potential difference may decrease or increase depending upon the nature of the element. It may be that component may be a resistor or a battery. But when we have completely traveled the circuit loop and arrive back at our starting point, the net change in the potential difference must be 0. That means the algebraic sum of changes in the potential differences is equal to 0. For this we need to keep some sign conventions. We have to follow from some sign conventions. So, for example, if you take one loop, there is a battery here and there is a resistor and it has one more battery and one more resistor, and this is a loop A, B, C, D, E, F. So as we move around the circuit loop and measure the potential difference across the battery or across the resistor, and when we come back again to the same point, if we start from A, if we again come back to same A, the algebraic sum must be equal to 0. The sum of the potential differences and their algebraic sum should be equal to 0. How could the sign conventions be applied now? First sign convention: the EMF of the battery is taken as positive when we move from positive terminal to negative terminal across the battery. The EMF of the battery is taken as positive when we move from long line to short line. You know the symbol of battery is like this. So when we are moving from positive to negative like this, then the EMF of the battery should be taken as positive. Second sign convention: EMF of the battery, EMF of the battery is taken as negative if we move from negative terminal to positive terminal. For example, from like this, and if you are moving like this from negative to positive, then the EMF of the battery is taken as negative. That is second sign convention. And the third sign convention is the direction of electric current should be observed. Sometimes it will be given like this, sometimes it will be like this. The direction of current should be observed. The direction of the direction of electric current should be observed. And now fourth sign convention is the potential difference across the resistor. The potential difference across the resistor is taken as a negative when we move along the direction of current. When we move along the direction of current, or we can say in the direction of current. If your loop is moving in this direction and the current direction is also like this, then we can take it as negative. And the last sign convention is the potential difference across the resistor is taken as a positive if we move opposite to the direction of electric current. The loop direction is like this and the current direction is like this. We have to take it as positive. So we have to apply all these sign conventions for our loop. So how to draw that loop? How to draw the loop? So what is important here? First one, the EMF of the battery is taken as positive when we are moving from positive to negative, like this. And EMF of the battery is taken as negative when we move from negative to positive. And third one is we have to apply the direction of electric current. Fourth one is potential difference across the resistor is taken as negative if we move along the direction of current. Means if the loop direction is like this and if the current direction is also same, then we have to take it as a negative. And if it is opposite, we have to take it as positive. So these are the rules what to be followed to solve the problems on loop law. Okay, I hope you understand. Now let us take one example of a loop. Let us take one loop here. We have a battery with one resistor, okay, and it's a simple loop, right, without any more components in the circuit. Simply we have here battery V is plus, this is minus, and the current direction is like this, and we have the current here I and here R1. And the loop is designated as A, this point is B, this is C, this is D, and this is E. If you take a simple loop like this, okay, if you take a simple loop like this, say A, B, C, D, E, A. So a loop means to start with one point and should end also with the same point. Then it's called a loop, A, B, C, D, E. Now here there is another direction of current like this. Okay. Now in this loop, the loop direction is like this: A to B, B to C, C to D, D to E, and E to A. Okay. Then the potential difference, or we can say EMF of the battery, of battery is given by V. It is plus or minus because the loop is moving from A to B like this, and we have to move from plus to minus, so minus V. Similarly, now from B to C we have R1, but we should take both R1 along with the I. V is equal to IR, no? So we have to take always both. So, and the loop direction is from B to C like this, and current direction is opposite. So we will take it as positive plus IR1. And from C to D we have nothing, and D to E is nothing, and E to A is also nothing. So this is the final answer, equal to 0.